Okay, in this tutorial we're having a look at solving systems of equations. Okay, so in the scope of the course this could be either with 2 variables or 3 variables, but in reality the same methods apply for as many variables as you like. Okay, so for 2 variables, this is the situations we can have. Okay, we can be trying to find a unique solution where our 2 lines just cross at some point. Okay, when that's the case, our gradients do not equal each other. Okay, and our c values, okay, if we're talking about y equals mx plus c, our c values can be equal, but they don't have to be. Okay, in this case it looks like they are equal, okay, but they wouldn't need to be. For no solution, that means that our sets of lines look like train tracks, so that means that our gradients must be the same, okay, and that c1 does not equal c2. Can't happen, okay, otherwise we'd have this case, which is infinitely many solutions. That means our 2 lines are in fact exactly the same, so m1 equals m2 and c1 equals c2. Okay, so our 3 types of setups that we can have. Okay, and you'll see that you can be asked questions on all 3 sorts. Okay, similarly with 3 variables, we'd have a unique solution. So that's when we've got our 3 planes here now. Okay, because we've got x, y, and z. We've got 3 planes that we talk about, not just straight lines. Okay, and you can see here that we've got this red one, the blue one, and the black one, and they all intersect each other at one point right in the middle. So that's our unique solution. No solution means that they're sitting above each other, kind of like pages of a book stacked up, but they're not actually touching each other. Okay, or we can have this situation where the red and black meet along this line, but the blue doesn't. The blue and black meet over here, and the blue and red meets over here. There's actually no unique solution there either. Okay, infinitely many solutions. Again, we've got 2 different options here. Okay, it can kind of look like the pages of a book for our different planes here, where they actually all meet down this centre line here. So they meet in infinite many locations there, or in fact that our 3 planes are exactly the same and they're all just stacked on top of each other, taking up exactly the same space. Okay, so that's what it can look like. Okay, but we actually need to look at some examples of how we actually solve these things. Okay, so we'll go our first one, which is our 2 variables. Okay, so we want to find the value of k for which the following equations have a unique solution. Okay, unique solution. So looking here, okay, and here's our equations. We've got kx plus 3y equals 1 and 4x plus 3ky equals 0. Okay, so I actually got 2 methods for solving these ones, and you'll find that method 2 can actually be quite useful at times. So when we're looking at unique solutions, that means that our gradients are different. Okay, now c values can either be the same or different. That's actually not that useful to attack this this question in that way, because a unique solution where our gradients are different, well, there's actually any number of ways to have a unique solution, because there's any number of ways to have 2 gradients that are different. So what we actually want to do is find the values for which the gradients are the same and then exclude those values. So what we want to do for our first method, okay, over here, is we're going to put them both in the form of y equals mx plus c. Okay, so we'll look at this first one. So we can say we've got 3y equals negative kx plus 1. So y equals negative k on 3x plus 1 on 3. Okay, so all I've done is I've moved the kx across this side by taking it away, and then I've divided everything by 3. So that's one equation. Okay, my second equation is this one here. I'm going to do a similar thing. I have 3ky equals negative 4x. And I'm going to say, well, y equals negative 4 on 3kx. Okay, this is equation 2. Now what we're going to do is, remember I said that there's an infinite number of ways of having the gradients different, so we're going to look at when they're the same. So we're simply going to say that negative k on 3 equals negative 4 on 3k. We're going to solve this equation now. So we're going to multiply this side by 3k, which will give us negative 3k squared. We're going to multiply this side by our 3, which will give us negative 12. Okay, now we're going to divide by negative 3, gives us k squared equals 4. Okay, so k then equals the square root of 4, which very importantly is going to be plus or minus 2. Okay, it can be plus or minus 2, so I've got to be careful there. Okay, So we've found the k value for which we actually get the same gradient. Now we've just got to specify that because we don't want the same k value, so we say then that k is an element. Okay, this means that we include these values, okay, of R, excluding the points -2 and 2. Okay, so any time that k is a value other than -2 or 2, we're going to end up with a unique solution, because when it's 2 or -2, then our gradients are the same, and we're not going to get a unique solution. Okay, oh sorry, we've got a second method of this one. Sorry, that's right. Hey, second method. Okay, what we do is we look at this equation here, and we actually set it up as a matrix. Okay, using the coefficients of our x and y values. Now it's really important to note here that x comes first, and well, it doesn't have to be that x comes first and y comes second, but we need to make sure in both equations that our x is in the same spot. So it's our first term here and y is our second term here. That's important. It doesn't actually matter what happens with our numbers over here. Okay, so you look then at writing just our coefficients down in our matrix. So you have k, and then we've got 3, then we've got 4, and we've got 3k. Now, if you remember, with a matrix like this, we can say it's A, B, C, and D. Okay, and we can find the determinant of the matrix by doing AD minus BC. So if we actually do the determinant of this matrix, AD is going to be 3k squared minus our BC, which is 3 times 4, which is 12. Okay? And we've got to set that equal to 0. And then solve for k. So we'll get 3k squared equals 12. Okay, which means k squared equals 4. And as we saw a minute ago from here, that means that we're plus or minus 2, and it needs to be interpreted in the same way. Okay, but we actually done slightly different. You'll find that using the matrices, if you're comfortable with using matrices, okay, then this can be a really effective method. If you're not as comfortable using matrices, okay, then often this can be a better way, because you're probably seeing simultaneous equations a little bit more. Okay, which is all this is. Okay, so now we're going to move on to an example here with 3 variables. Now, I would recommend that unless you are required to use, or show working out, sorry, that you'd probably use a calculator for this. This is really a good example of using that technology. However, we can do it. Okay, so we're going to label our 3 equations here, which are 2x take 3y plus 2z equals 5. That's equation 1. X take 5y plus z equals 1 is equation 2. 2z plus 3y plus z, sorry, 2x plus 3y plus z equals -2 is equation 3. Okay, so what we need to do is really a process of elimination here. Okay, so we're going to look at the fact that we've got 2x and 2x here and 1x there. So what we're going to do is we're going to say we're going to do equation 1, take away 2 lots of equation 2. Okay, so we're going to 2x, take 2x, because remember I'm multiplying this whole equation by 2. It's going to leave us with no x. Then we've got minus 3y, okay, take away 2 lots of -5y. So 2 lots of -5y is -10. Okay, we're going 3y, take -10 is going to give us positive 7y. Okay, and 2z, take 2z, okay, means that we're not going to have any z left. Right? And in fact then we can go -5 take 2, because we've got to double it, remember, gives us -7, and simply from here we actually say that y equals -1, which is really convenient actually. We're very lucky that they actually work like that. Most of the time it won't, but that's okay. Now we'll do the same thing again with this equation and say we're going to do 3 minus 2 lots of 2. Okay, so 2x take 2x will leave us with no x. That's the whole point, we'll get rid of it. Okay, then we're going to say, well, we've got 3y, take away 2 lots of -5y, will leave us with 13y. Okay, and then we're going to have z, take away 2 lots of z, will leave us with -z. and then minus 2, take away 2 lots of 1 will leave us with negative 4. Now this is quite nice because we actually know that y equals negative 1, so you can put that in. And so we've got negative 13 minus z equals negative 4. Okay, so we can say that negative z is going to equal 9 here. And so z equals negative 9. Okay, so we're getting there with this. Okay, now that we know that, we can sub our y and our z values back into an equation to work out what x must be. Easiest one is going to be subbing it into here. Okay, so we say x minus 5 lots of y, which is negative 1, plus z, which is negative 9, equals 1. So we say that x plus 5 minus 9 equals 1. So x take 4 equals 1. So x equals 5. Okay, so we've gone through a bit of a process of elimination there. Now this one happened to drop out a value straight away of y. Now often that won't happen. Okay, if that doesn't happen, it's just going to be that process that we go through of eliminating variables then until we get down to just one variable that we know and subbing them back in. Okay, so look, hopefully that helps you out with a bit of this work on our systems of equations.